Chapter 12 is about gases, and in this chapter we're going to be looking at how different variables come together to create the pressure, temperature, and volume relationships we see among gases. So our ultimate goal here is to be able to understand the mathematical relationships that happen in any given sample of gas and the changes that those variables undergo. So in 12.1, we first have to learn about atmospheric pressure and how barometers work, and then we're going to talk about various units of pressure. So when we think about pressure, in mathematical terms, it's force divided by unit of area. So I always like to tell people to think of this as putting your finger down on the table and pressing down. You are putting a certain pressure on a small area of that table or countertop or wall, whatever you're pushing on, and that is creating pressure on that surface. If you put your hand flat down on that surface, you're also creating pressure, but you're creating a different type of pressure because you are spreading out the force that is being put over a larger area. Pressure is measured with a tool called a barometer. So you've probably heard this maybe in the weather, the barometer is reading this or this. It's a measure of the air pressure of the atmosphere. And it quite literally works by pushing, the atmosphere is pushing down on a pool of mercury. So we see the atmosphere pushing down on this open pool. And as a result, the mercury gets pushed up this tube. And when it gets pushed up a tube, pressure is quite literally read in millimeters of mercury. So you can see here, this is reading 760 millimeters of mercury that are being pushed up this tube. And depending on the weather app that you use, you could open it right now and see, I'm looking at mine. Mine says the pressure right now is 30.30 inches. It says inches Hg. And that's just because we don't use the metric system. So our units are in inches of mercury, but millimeters of mercury is a more appropriate version of that unit. A manometer is a little bit different. It measures the pressure of a gas in a closed system. So what I want to focus on is these two pictures to the right. And they show us that we have an open end to one side of this manometer. We see our enclosed gas in the center. So we're going to have our atmospheric pressure pushing down on this open end. Again, this is a column of mercury because it's measured the same way. It's read the same way in millimeters or inches of mercury. And then what we see is this gas is pushing up against that column. So as it pushes down on this column of mercury, the atmosphere is also pushing down on this column of mercury. So what we're going to see is a difference. One of them is going to be pushing harder on that column of mercury. So here we can see that the atmospheric pressure is pushing just a little bit more on that column of mercury. So if we say that our atmosphere is 760 millimeters of mercury, and then we know that this height difference is 10 millimeters of mercury, we know that our atmospheric pressure is going to be 10 millimeters of mercury more than the pressure of the enclosed gas. So if we subtract that 10 millimeters of mercury, then we will be able to see that the temperature of our enclosed gas is 750 millimeters of mercury. Now it works the same way when our gas is pushing more. We can see in this case that our enclosed gas is pushing more on this column of mercury than the atmospheric pressure is. So this one is going to be a little bit different. If, again, we have the same atmospheric pressure of 760 millimeters of mercury, and again, we know that this difference is 10 millimeters of mercury, then in this case, what we would see happening is that since the enclosed gas is greater than our atmospheric pressure, we would then have to add that 10 millimeters of mercury, and that would give us an enclosed gas pressure of 770 millimeters of mercury. So depending on which one of those is greater, we know we're going to either have to add or subtract based on the atmospheric pressure. We use different units to measure pressure, so we already talked about the difference between millimeters of mercury and inches of mercury, but there are several other units that are used depending on where you are, the circumstances, and whether or not you're publishing an article. So 1 atmosphere is what we are going to be using most frequently. And an atmosphere is just like it sounds. It's an atmosphere pressing down on you, the air around you pressing down on you. So if we are at sea level, that is considered 1 atmosphere of pressure. It's all of the atmosphere combined on the planet pushing down on us. If we were a little higher than that, if we were up on a mountain or at a higher elevation, we would have less of the atmosphere pushing down on us. So the pressure would actually be less than 1 atmosphere. If we were below sea level, more of that atmosphere would be pushing down on us. So at that point, the atmospheric pressure would be more than 1 atmosphere. 1 atmosphere is equal to 760 torr, or 760 millimeters of mercury. Now, this relationship tells us that 1 torr is equal to 1 millimeter of mercury. 101,325 pascals, or 14.69 psi. Now, we use psi a lot here, especially when we're talking about tire pressure. So psi stands for pounds per square inch, which makes sense in terms of what we talked about, like putting your finger on the table and how that represents pressure. I'm exerting a certain number of pounds per square inch of surface that I'm pushing on. The Pascal is the SI unit. So we talked about the SI unit being the International System of Units, and this is the one that you're going to use if you're publishing a paper. Remember, we want all of the systems to be able to meet in one publishing language so everyone can communicate with each other, and that's what the SI system is for. So the Pascal is the SI unit. If we wanted to convert, we could convert 28 psi to ATM, torr, and pascals. Now again, this just uses the conversion method that we've been using up to this point, dimensional analysis. So we always start with our given piece of information, and we're going to start with 28 psi, and we're going to convert that to ATM. So we draw our line. Remember, that line reminds us that something is going to go on the bottom and something is going to go on the top. What's going to go on the bottom here is psi. Remember, we want those units to cancel out. So whatever was on the top of the previous conversion factor must be on the bottom of the next conversion factor. I'm converting to ATM, so I'm going to put ATM on top. And I know, based on the previous slide, that the conversion factor here is that 1 ATM equals 14.69 psi. So if you've lined out the units, all you have to do is pair those numbers with the correct units in your conversion factor. At this point, I can stop converting because I've reached my desired units of ATM. PSI cancel out. And when I plug this in my calculator, the 14.69 is on the bottom, so I'm dividing 28 by 14.69, and as a result, I get 1.901 ATM. I'm doing the same thing again, except this time I'm converting PSI to torr. So same process though, I'm going to put PSI on the bottom. I'm going to put torr on top, and looking back at my previous conversion factors, I can see 14.69 PSI is 760 torr. PSIs cancel. This is a multi-step calculator problem here because I have a number on the top and the bottom. So I'm going to multiply 28 times 760 and then divide that by 14.69. And this is going to give me 1,448.6 torr. Notice here I'm not observing sig figs. The last part of this problem is asking me to convert PSI to pascals. The 28 PSI, draw the line. Something has to go on the bottom. That something is PSI. And on top, I'm going to place pascals. According to my previous conversion factors, 14.69 PSI to 101,325 pascals. PSIs cancel. I'm left in my desired unit. What I'm going to plug in my calculator is 28 times 101,325 divided by 14.69. And this gives me 193,131 pascals. So now that we have a little background into what pressure is and how it's measured, we can start looking at the different gas laws. So each of these gas laws is going to relate two variables to each other. And then we will be able to see through manipulating one of these variables or changing the conditions what is going to happen to the other variable. So for 12.2, we have two aims. The first is to understand the law that relates the pressure and volume of a gas. And then the second aim is to do calculations with this law. The first law that we're going to look at is Boyle's law. So you can see in this picture there are a couple of things happening, or that appear to be happening. One of them is you can see the box getting bigger and smaller, and it's oscillating. We can see at this point it's getting bigger, and then when it reaches its max, it's getting smaller. So what we can see happening when this box gets smaller is these molecules appear to be moving faster. Now, they are not moving faster, but what is happening is they are hitting the walls of their container more frequently. Remember, pressure is exerted every time one of these balls hits the side of its container. So the more times these balls hit the sides of their container, the higher the pressure we see here. So what we can say is when volume decreases, what is happening to the pressure? We see those balls hitting the sides of their container more, and then as a result, the pressure is going to increase. The container shrinks or the volume decreases. Those balls are atoms, gas molecules, are hitting the sides of their container more frequently, and as a result, the pressure of this system increases. So in words, when we're at a constant temperature, again, we are not talking about molecules moving faster. That's not a factor here. So when we're keeping that temperature constant and having those molecules move at the same speed, volume and pressure are inversely proportional. So we've talked about this word inverse before. When we were looking at inverse fractions, we were flipping the fraction or taking the opposite of that fraction. And that's what we see happening here. P is pressure, V is volume, so we see that when pressure increases, volume goes down. And we can also see that when pressure decreases, volume goes up. So we see an inverse relationship happening here. When one goes up, the other one goes down. When one goes down, the other one goes up. They behave in an opposite manner. They do opposite things. So what we want to look at here is the fact that P times V equals K. And what K is referring to is just this specific set of conditions for this gas. So if I have a gas in a container, pressure will be at a certain numerical value and volume will be at a certain numerical value. Now, this statement is also true. If P times V equals K, K equals P times V. Now we're setting it up this way so we can set the stage for before and after conditions. So it makes sense that if pressure times volume has to equal a certain number, then after we manipulate one of those variables, that combination has to stay the same as well. So this means the before and after conditions have to be equal for the same gas, which is what allows us to say that if we manipulate one, the other one will be manipulated in the opposite direction. The whole point of this is to maintain that specific set of conditions, because remember, we are at a constant temperature, so we can't change other variables. So the first problem asks us to consider a 1.5 liter sample of CClF2 at 56 torr. If the pressure is changed to 150 torr, will the volume increase or decrease? So the first thing we want to do is approach this from a purely conceptual standpoint before we do any sort of calculation. This allows us to check our answer at the end and make sure that the answer we get makes sense. So identify your variables really quickly. So we've got a volume, we've got a pressure, and then we've got another pressure. So what do we see happening with the pressure? The pressure is changed to 150 torr, and it was initially at 56 torr. This means the pressure has increased. So what do we expect to happen to the volume? We expect the volume to decrease as a result of this change. Remember, the whole point is to maintain the conditions that were in the before situation. So what is the new volume? At this point, we know we expect our volume to decrease, so we hope that our answer will give us a lower volume than we originally started with. So here we want to define our variables. We have P1, V1, P2, and V2. Our P1 value is 56 torr. Our V1 value is 1.5 liters. Our P2 is 150 torr. And our V2 is our unknown variable. That's what we're being asked for. Now, could we say that P1 and V1 are 150 and unknown? Yes, it doesn't matter which side of this equation you put these numbers on. What is important is that you pair them together. And this keyword at here tells you that 1.5 and 56 need to be paired together. So remember our equation, P1V1 equals P2V2. So what we want to do is rearrange this equation to solve for our V2. The other method could be just to plug all of your numbers in and then solve for X, but I like to rearrange it initially just to give myself practice rearranging for these variables. So we're plugging in our values. Our P1 was 56, our V1 is 1.5, and our P2 is 150. And if we've set it up this way, all we have to do is plug this into our calculator, and we've solved for V2. 56 times 1.5 divided by 150 gives me 0.56 liters. Remember, if the unit that gets put in is liters, the unit that's going to come out will also be liters. So conceptually checking our answer, we said in the beginning that the volume was going to decrease as a result of increased pressure. We do see that 0.56 liters is less than 1.5 liters. So that's a quick way to check your answer to make sure you're correct. The next problem. An engine has a volume of 0.725 liters. After the piston moves, the volume is 0.075 liters. The fuel-air mixture is initially at a pressure of 1 atm. What is the compressed pressure? So a lot of people will look at this and automatically just stop reading. There's too many words. It's a word problem. I don't know what's happening here. Instead of just immediately panicking, identify your variables. What is your P1? What is your V1? And then if you recognize that you have all of the variables you need to satisfy a certain equation, approach it from that perspective if the words in here are freaking you out a little bit. So we see that the pressure, the only pressure we've been given is 1 atm, and that's because we're trying to find an unknown pressure. So this time we have two volumes. Our volume 1 is 0.725 liters. And that's the initial volume we've been given here. And a way to organize these, it is going to be helpful reading the problem to be able to organize these, because it says after the piston moves, and then it asks us for the compressed pressure. Remember, compressed means to shrink. So if we have shrunk the volume, the pressure, they're asking us for the pressure at the compressed volume. So we know that we are starting, because it's initially at a pressure of 1 atm and 0.725 liters. So the words in the problem will tell us, or will confirm with us, how to assign each of these different variables. Our pressure 2 is our unknown value. That is what we're solving for. We don't know that value. It's asking us to find that compressed pressure. And after the piston moves, the new volume is 0.075 liters. So we want to set these up again in our similar equation, P1V1 equals P2V2, except this time we are solving for P2. So P2 is P1 times V1 divided by V2, and solving for X, remember that's just dividing both sides by V2, and we see on this side that V2 ends up canceling. So now plugging in our values for our variables, we have 1 atm times 0.725 liters divided by 0.075 liters, and that gives us our P2 value. And remember, what we expected to happen here, since the volume decreased, is an increase in pressure. And in fact, we see that the pressure went from 1 atm to 9.67 atm. Again, the unit we put in is the unit we get out.